In lesson 8 in Math 222, I'd like to do a couple of things. One, I'd like to do some L'Hopital's rule applications where the limits are more advanced. So we'll do 3 examples in this screencast that are a little bit more advanced. When we get to class, we'll hit this idea, and then we'll also take a look at some inverse trig functions and their derivatives, and that will be the last thing that's covered on exam 1. So I have I have 3 examples for us. And they are as follows. Let's find the limit x approaches infinity of x times the tangent of 1 over x. It is not immediately apparent that this is a L'Hopital's rule question. As x gets large without bound, x gets large without bound. As x gets large without bound, this angle approaches 0. The tangent of 0 is 0. What in the world is infinity times 0? Because that's not really 0, it's just a small positive number. And infinity is not a number, it just gets large without bound. And how can we even use L'Hopital's rule anyway? This is not a quotient, so what do we even do with that? And the answer is we make it a quotient. L'Hopital's rule requires there to be a quotient. It's complicated not to have the tangent function up top, but multiplying by x is the same as dividing by 1 over x. Now we have a quotient. The numerator goes to 0. The denominator goes to 0, and so we can use L'Hopital's rule. L'Hopital's rule says we take the derivative of the numerator, the derivative of the denominator, try again. Derivative of tangent something is secant squared of that something times the derivative of that something. The derivative of 1 over x is negative 1 over x squared. The negative 1 over x squareds drop. As x gets larger and larger without bound, this angle gets closer and closer to 0. The secant of 0 is 1, which squares to 1. Since this limit is 1, this limit is 1. So sometimes when you don't have a quotient, but you're still an indeterminate form, you can make that a quotient and use L'Hopital's rule to evaluate. Find the limit as x approaches 1 of x to the power of 1 over x minus 1. What in the world do we do with that? Because as x approaches 1, this base approaches 1, but that exponent approaches infinity, and that's not really 1, it's just a number close to 1, and infinity just means it gets bigger and bigger and bigger. So what is this thing? Well, how do we deal with this? See, this exponent's really high, and I don't want to deal with that. I mean, as an exponent, that's just tricky. So I want to do a completely different problem. I would like to consider instead the limit of the natural log of 1 over x minus 1. I would like to do a completely different problem. Why? Well, because if you include the natural log, then this comes down in front. Right? But wait a minute, that's a fraction. That's a fraction. And it's a fraction whose numerator and denominator both go to 0. So by L'Hopital, this is that. And what does that turn out to be? As x gets closer and closer to 1, this gets closer and closer to 1. So the natural log approaches 1. If the natural log approaches 1, then this limit approaches e to the 1. And that's your answer. So in this case, we have a base to an exponent, and this is some indeterminate form. So that's hard to work with because exponents are hard to work with. So we use the natural log to knock the exponent down. L'Hopital takes us home, and then we reverse the logarithm process. Oh, I did it the third time. I'll demonstrate that one more time. Limit as x approaches infinity of the natural log of x to the 1 over x. Again, as x gets larger without bound, the base gets larger without bound, the exponent gets closer and closer to 0, and so you're thinking, well, I mean, it's infinity, so that gets big, and it's going to the 0 power, so that should go to 1, but it's not really 0, it's just close to 0. So does the infinity beat the 0? Does the 0 beat the infinity? Like, how does that all work? And I don't want to deal with exponents at all. I want to do a different problem. I want to consider instead the limit of the natural log of x to the 1 over x. And this is the natural log of x over x. Why? Because that 1 over x comes down in front. It becomes this fraction here. Well, this goes to infinity. This goes to infinity. L'Hopital says that we take the derivative of the numerator. Did you remember chain rule? Derivative of the denominator. And we try again. This obviously goes to 0. The natural log goes to 0. So this goes to e to the 0, and that's 1. So if you're looking for some practice on this, you're looking in Volume 1, Section 4.8. I would look at 382 and 392 and come to class ready to talk about that. Awesome. We will see you when we gather.